Okay, so I'd like to talk a little bit about the problems of a geometry for the biological sciences and the what I call sciences of intelligence. That means things like artificial intelligence and human intelligence. So what we already have, well, actually, I refer to Euclid for a long time. We have a geometry for the physical sciences. I'd say basically that's Euclidean geometry. And I'm not sure if people know what that is. In some form or other, everybody knows Euclidean geometry. But let me review my own definition. It's a mathematical definition. So I start with a vector space, say V, just an ordinary finite dimensional vector space. And Euclidean geometry is this vector space endowed with an inner product. So this is a vector space with a, well, a lot of people say dot product. So a dot product, I will usually write this notation, comma. So this has, for example, x and y, and this is just the dot product of x and y on this finite dimensional space. So this satisfies usual positivity symmetric rules. So that's Euclidean geometry. That's the definition of Euclidean geometry. And that has provided a framework for the physical sciences since Euclid. There are many extensions of this geometry through the centuries. In particular, let me mention what's called not due to Hilbert, but a Hilbert space. This allows one to let V be infinite dimensions. I won't worry about that here. Also, one has extensions to spaces that are curved. So we have Riemannian geometry, extending the geometry of Euclidean space. And we have Einstein-type geometries by taking Minkowski relaxation of the positivity here. So these are the geometries that give us a space to do physical sciences, roughly speaking. There's nothing like this for the biological sciences or, as I say, the sciences of intelligence. And I'd like to talk about something in the direction of defining such a geometry and explain how it could clarify a lot of things. That's what I wanted to do today. And the trouble is, in these sciences, the biological sciences, we don't have things given to us like manifolds or even Euclidean space. We have very frequently in biology, as I'll pursue, we have a set of genes. It's a finite set. So we have finite sets. On finite sets, surely Euclidean geometry does not operate on finite sets. Okay, and we have other kinds of spaces, all kinds of spaces from biology, vision, from robotics, which are, this structures are not equipped to deal with. Euclidean geometry doesn't work. So what I'd like to suggest is a way of extending Euclidean geometry in a way which makes sense for these spaces, especially finite spaces, because data is described in terms of finite spaces, and data is preeminent because of the computational aspects of the sciences I speak of. So the idea of extending this Euclidean geometry, finite spaces, is a big part of what I want to speak of. I'll give general principles and then three main examples. The three examples I want to speak of are document classification, Google type problem, document classification, and vision, and especially, this will be especially developed in the next two talks, but also somewhat here, this would be genes and their variations, peptides. These are candidates for immune vaccines, and so on. This is immunology, the last one. So we have immunology, vision, and document classification. And we'd like to extend this Euclidean geometry so it can elucidate and clarify these sciences. So up here we have Euclidean geometry. So maybe I should, first of all, give just the basic principle of how one can do it. And it's very, very simple. You know, I think if you're thinking mathematically, it's easier. But even if you aren't mathematicians, maybe you can still see it because of the simplicity of extending Euclidean geometry to these spaces. And let me do it for a finite space, for example. We'll be working with finite spaces here mostly. Okay, so finite spaces come up in all these situations, especially data. All right, so we have the space X. And there's two ways of looking at this. X is a finite space. And there's two starting points. Let me start with this picture of what you might call a feature map. Phi goes from X into, let me say, R. This is the real numbers, but I want to take coordinates over X. So I say R product Ri. I belongs to X. So in other words, I want to consider the space of, say, X. Yeah, let me write it this way, X1 up to Xn, where n is the number of points. N equals, I write it this way, the number of points of X. And the points of X are referred to by these subscripts. Okay, so what we could do then is if we take X, we could just map it into the space of features. So we could say that phi of I equals X sub I is just the I's coordinate vector of this space. So this space is Rn. Or I could write it in different ways, R sub X. Okay, so that's the Cartesian space. And so I can think of a feature map as going from a point of X into a real number, X sub I. So you could think of this space as just being a coordinate space of n variables. Okay, so we could start with a feature map. That's one point of view of this construction. Okay, so this feature map could be the features of an element here. We know that a lot from data sets. We're given features of each point in some set, X in this case, and we write down the list of features. Like, for example, patients would have an age. That's one feature. A weight, another feature, and so on. So if we do that, I can now, suppose we're given this feature map, this list of features of each element of X, I can define a Euclidean structure, K. This inner product I will write sometimes K inner product like this, XY. K is going to be connected to a certain function K on the product space. And then we define K in this case, K of X, Y equals sum phi I, we can write this way, Xi, Yi is just the dot product description, I going from 1 to n. and then I divide by n to make an average here. Okay, so this is defines an inner product. So that's a construction which associates to a finite set given features. It defines a Euclidean geometry. I think this is a good example of how we could get a Euclidean geometry associated to a finite space once we have some feature map, a list of features. All right, so let me give a description I'm a little more used to. I wanted to start with a kernel K on X, finite space X. And I want to identify that with a different approach, which is equivalent in some sense, but conceptually different. So we have a kernel on X. I want to define that, and that is the dominant aspect of what we're doing in all these pictures. So K, a kernel definition, is a map from X cross X into R, make it R plus, positive reals, which is symmetric and positive definite, where X is just a finite space. Okay, so I do that, and most people would say fine, but there is a slight formality here. To make sense of this, one has to say, what does positive definite mean here? Okay, so what one can do is to take any ordering of the points in X. If we take an ordering of points of X, say by I equals 1 to n, that will give a matrix representation for K. And now we say that K is positive definite, and that will be positive definite independent of the ordering. Okay, so this is the basic object, this kernel with which we develop. And this gives an alternate construction of the inner product, and one can go back and forth from the two representations of this Euclidean structure given a finite set. Okay, so the upshot is, given a finite set, I can start either with a kernel or a feature map and give rise to a Euclidean space. Here we can write down now on the space R. Let me write Rx still. This is just this is just Rn, where we're indexed by given an order on X. And so we can write the inner product. Now we have to be careful of our notation. I can write the inner product of X, Y equals simply K. Wait, let me do this a little more slowly. Yeah, so we have to be a little more careful here. What I want to do is start with a kernel. And then I want to write down a space of functions H. This is all space of all functions on X. It's a finite set. So this is a finite dimensional vector space of the same dimension as the space X. So this is just a space of functions. And now I want to write an inner product on H. Okay? What? Yeah, functions on X to R, right. R-valued functions. R-valued here. Right. So I'm getting a vector space, a real vector space. Okay, so I want to define an inner product. That's going to be associated to the kernel K, and I do this as follows. I'm going to define Kx, a function on X, defined by Kx of Y equals K of X and Y. Okay, so for each X in the space capital X, I'm defining an associated real valued function by that formula. And now what I write here is this defined by k, the inner product of kx, ky equals k of x and y. You can forget all this for the moment and just look at this board here. So I'm given the kernel, then I can write down these basis vectors. As x goes over x, this forms a basis for the functions on x. Same here. And so I take the inner product of these, get simply this way. And that's extended linearly to all functions. Okay, so this is this shows why a kernel K can develop into a Euclidean space, real Euclidean space. Then in a sense, you can turn it around to define phi here by k sub x and get a reverse process. But I think maybe it's simpler just to keep this in the back of your mind. And what I want to do, everything is right here. So given a kernel, then we have a Euclidean space. Given a kernel on a finite space, we construct Euclidean space. So that's the theme that I want to illustrate as to how we go with a kernel in these spaces which are finite, data and so on, peptides, and we get a Euclidean structure associated to that once we have a kernel. So this gives us the problem, find a good kernel. So this is the problem of finding a good kernel. A good kernel is one that corresponds to reality in some contexts like these. So once we have a kernel, then we have a Euclidean geometry. And this construction is lying in the background. In document classification, there is an algorithm, very simple and old, called bag of words. Okay, so I want to show now, and this illustrates everything I'm saying over here, bag of words. Okay, so for bag of words, I start with a dictionary. So this is very standard, and we can elaborate quite a bit in our context, but you see how document classification becomes a problem in Euclidean space via this construction here. So I take a dictionary. That's just going to be some finite set of words in the language we're using. Say English, and we want to classify English documents, English language documents. And we have a dictionary. Dictionary could just be Webster's dictionary or a short, small dictionary. Okay, so we have a dictionary. Let me call the dictionary D, finite. And then we have some sentences, let me call F, will be documents. Small or big. We want to see the principle of how this classical algorithm works here, bag of words. Okay, so we have a dictionary D and a set of documents. So we want to put a kernel on D. So we can define K from D cross D into R plus. Okay, so just for simplicity, we can say K of X, Y equals 1 if Y equals X, 0 otherwise. I think in the original bag of words, that's effectively the kernel used. I mean, that bag of words is not described the way I do it, but it's equivalent. And now we're allowed to make a much more general picture. K is supposed to be something like a similarity. So we could say K of X and Y is close to 1 if X and Y are synonyms. X equals Y and K of Xi equals 1. Or we could say that there's a matter of degree. How far is the word X to the word Y? So there's a set of gradations here between 0 and 1, say, given by this kernel I've just written down. It's we can well imagine this is symmetric, especially if I take this definition, symmetric and positive definite. This is just the identity matrix in this case. But it can be elaborated to have something much, much more sensible. All right, if you do that, now we take a map from F into R X, but as follows. This is going to be a map, it's called N. This would be a map from sentences, or better than sentences, documents, into the space of N variables, where we have N words here. Dictionary D of N words. Okay, so this N is something in vision we've called the neural response. So we want to say that N of a document, NF, so here we have F, a document, and we want to say what that is at the coordinate, let's say W. So W belongs to the dictionary. This is equal to the number of times W occurs in F. So it just counts the number of times that this document contains the word W. Dictionary is going to be a dictionary of words. Okay, so this is, envision this would be called the neural response. And here, what does that mean? Well, this gives a way of comparing F and G. If we have two documents, F and G, that have a comparable number of words for a dictionary, then those documents are likely to be similar. So that's the idea. The idea of these kernels and Euclidean space is to give similarity to their elements. So this is the way we do this. This has aspects of a feature map, but here we're talking about these spaces. So this is sentences, or I should say documents with values in a space whose coordinates are given as the words. And the coordinate is given the number of times the word W, we take coordinate W, so yeah, so this is the Wth coordinate of this map, NF, and it's going to be defined by just counting the number of words W in that document F. Okay, now we can take the kernel of F and G equal, and it's very close to this construction here. It's just 1 over N sum over the words in the dictionary of N, F of W, and G of W. Okay, and that's going to give us a kernel K on F. So F and G are documents or elements of F. So this is the construction of a kernel on the space F. So that puts it on this. Yeah, so that puts an inner product on the corresponding Euclidean space given by these neural response maps. It could also be interpreted in two ways: as an inner product on the Euclidean space or a kernel on the space F. This could be interpreted as this is a kernel on the space F. It's easy to check. So here is an example of a kernel. And this exactly gives us similarity between when are two documents similar to each other. For document classification, this kernel defined this way is the old bag of words, which was used for a long time in document classification. Okay, so and one can expand this by taking a more sophisticated dictionaries, more sophisticated similarities at this basic level. See, we're starting with a kernel at the basic level of words. So I should really call this K1, then I could call this K2. So we have initially a kernel K1 on words. And this gives rise to a similarity or a kernel K2 on the documents. And this is the something which becomes a very important principle in what we do in immunology and also in vision. We go from kernel, so to speak, given by nature on the smallest units. So we assume a kernel to begin with just on the very smallest units like words, or in visions on small patches of images. And from that, this construction will give us a kernel on the general space we're looking at. So this goes from what we call, something very, very local, where we can really say things are close. Two images, if they're close by images, it makes sense to talk about their distance. But this gives something more. This construction goes from, as I say, from words to documents. Okay, so I think this is a fairly intuitive illustration of this idea of using kernels and Euclidean structures in intelligence. Because here we have these finite sets in this construction, and we get going in using Euclidean structures to get similarities on important objects, for example, in Google. On my websites, you'll see nothing on immunology. That paper is just being finished, but there is a paper on the neural response. I think 4 or 5 of us wrote that. That's published in the FOCM journal, and that's got a big development of these ideas in vision. This algorithm is, in this group in immunology, we've developed this a little bit, so it works good for document classification. So we have a good development here, which is just a little more complicated, but gives results on document classification, which are pretty good. Okay, so in vision, we take a dictionary. This is vision now. A dictionary as follows. These are going to be small images. Images, just it could be things like this, or a little bigger too. But some basic images are in the dictionary. So this would be what we call D. These would correspond to the words in the bag of words. It could be expanded to contain images which are a little bigger. We could put in an image like that, and so on. And then we have the basic space F is the space of images. Images, you can think of just photographs, pictures, and database of pictures or photographs. And now what we did in this paper that you can read is the same construction. So we define a space N from the space of images in a certain context, into, again, we write R defined by, these were called templates in the paper. T belonging to a dictionary D. Then we make exactly the same construction. And just to make this a little more pictorial, if you see if something like this occurs, then you can begin to read off a picture. For example, if you can read off from the neural response, for example, something like this. In the picture, this will trigger a response in this map, and then you might trigger another one like this, another like this. And see, just a few of these responses give rise to a suggestion, even with my bad artwork, of an image. So the idea is if you do this more systematically, you get a scheme for pattern recognition. That's what we do. But this is the core idea. Okay, so in fact, this development here I did with Tommy Poggio and a few others, especially Tommy Poggio and I worked on this. He's a person working in neurophysiology at MIT, especially in vision. And we spent some years developing this notion of vision, and that's all written down and published and on the website. But then that suggested this development we're using now for immunology. Okay. So let me then pass to the immunology situation, where we'll be doing this in also the next lectures to give a more deep and substantial development of these same ideas. So now we're looking at immunology, and we want to eventually look at things like the peptide binding problem and classification of diseases according to genes, problems like this. So we spent a group of these people, Xiao, Raymond Wong, Chin Wo, this is in Hong Kong, and Shen Wenjun, and myself. So this is the group that we've been working with for almost 2 years. And we haven't published anything yet, but we're trying to get a paper ready for this meeting, and I don't think we'll quite succeed, but close. Okay, so in that situation, for immunology, we're going to follow the things that I've just been talking about, but everything is going to be done in very careful detail. So the dictionary, in this case, it's maybe more natural to call an alphabet. It will be D, but we'll call it A. And it's going to have 20 elements, and these are the 20 amino acids of basic for all of life. So A equals a set of 20 amino acids. Okay. The idea is that all proteins can be thought of as some kind of combinations of these 20 amino acids. Okay, so we're going to start with this dictionary of 20 amino acids. This is a little bit closer to the bag of words, but it's going to be somewhat more sophisticated. And now we have a kernel, K1, on A. So since the amino acids are so central in medicine and biology, human biology and animals and so on, there have been many studies of similarities on the set of amino acids. It's such a fundamental problem. There are 100 different candidates for K1, similarities or kernels on A. Each one has a paper in a biological journal, so there's a vast literature on these kernels. Okay, so what we did was to study a lot this literature, and we came up with a particular kernel called Blossom 62. Okay, so that is going to be a kernel on A. It's going to be a symmetric function on the product space, and it's going to have this positive definite property. So one reason why this is important, this positive definite property that we're using here, is because this defines a Euclidean structure, which is so basic to physics. So positive definite is a key property for us and for this whole idea of passing to use of Euclidean spaces in biology and intelligence. Okay, so of all these 100 papers, we have never seen one which ever checked about positive definiteness of these matrices. So that property has not, as far as we can tell, has not reached biology. So what we did, this is the most common similarity, Blossom 62. What we did was use a variation on this, and we did prove that our variation is positive definite. I'll go into detail of that maybe either today or next time, the description of K1. But it's a positive definite. It is a kernel on A. We get a kernel on A with a parameter. And that plays a central role in our analysis of eventually peptide binding and lots of other properties of classifying genes. But the starting point is this K1. And this generates everything else. Just like in a situation of a bag of words, we started with a kernel on the dictionary there, which is like the alphabet here, and we generated a kernel on documents. So this way, starting here, we generate a kernel similar to the bag of words, kernel on alleles, gene variants. So we get a kernel on that space. We have a kernel on, more generally, on amino acid chains. So amino acid chains we find quite central for so many aspects of biology. And proteins, which are central for what we do and central for life, they can be expressed in terms of a chain of amino acids. Just like a document can be expressed as a chain of letters in the alphabet, or a chain of words. So we can look at this object, amino acid chains. Okay, so these are going to be finite sets of amino acid chains, and much of our mathematical development deals with just the mathematics of a kernel on an alphabet and the generated kernels on the chains of that. So this is a fairly pure mathematical construction. It still requires quite a lot of mathematical thinking. And then we apply it to several examples in immunology, namely peptides, then alleles corresponding to genes which are related to immunology, and eventually proteins and bird flu viruses. All these have an expression as amino acid chains, and so what I want to define is a kernel K1 on all amino acid chains or finite sets of amino acid chains. So amino acid chain is just something of the form A1, A2, A3, AK, AL, say. Finite set of these where the AI are elements of A. So this is a lot of biology is already expressed in these terms. So these are things we're not making up or anything. This is already a setting which calls for a mathematical analysis. The analysis of similarities on amino acid chains. For example, if these were two different alleles corresponding to a gene, but represented in different people, we want to know about issues of transplants. So we want to know similarity of two amino acid sequences. If those two amino acid sequences are sufficiently similar, then the patient will accept the transplant from somebody with that similar expression for the gene. So this is a little sketch of the things we're going to do. So I want to define, starting with K1 on A, I want to define a kernel eventually on all of these amino acid chains. Or I should say finite sets of them. And then I will apply that to our situation, various situations in immunology. Okay, so let me say how that goes. It's just a sophisticated version of the other examples I've given. Okay, so it's going to be done, and this is, maybe I'll review it a little bit sometimes, but for the moment, let's assume we have defined K1 on the amino acids. Similarity matrix, if you want, or similarity kernel on the amino acids. And then I'll next propose the definition of K2. So we take K2 of U and V, where U and V have the same length, equals K, and U and V belong to A, in this case, A to the K. So they're chains. This is the product space of amino acids with itself, K times. So these are called K-mers in immunology. So we're talking about a new kernel, K2, on K-mers. Okay, so this is quite simple. So U equals U1 up to UK. V equals V1 BK. And so we just write here the product of K1 of UI VI I equals 1 to K. It's just the product. And by general principles, if K1 is a kernel, then K2 is a kernel. This is the tensor product kernel. I can write the K there. Depends on K. So this is K2. So this means I'm looking at smaller sequences of different lengths, but generally speaking, these will be smaller than the ultimate chains we're analyzing. So then I can write now K3 of F and G. Say F and G are just amino acid chains, no other restriction. And I want to define a new similarity, K3. This is our final similarity, and it's just given as the following. It's K2 of UV over K. U is contained in F, a substring of F. V is the substring of G, and we take this average over all K. Or take the average over all these numbers. So we just take the ordinary arithmetic average of these K2s to get a kernel K3. And remarkably enough, this is the ultimate kernel that we use for analyzing these problems in immunology. It's given just this amazingly simple way. Yeah, when I write K here, I mean the average over K. Mm-hmm. Yeah, so this is, really, we were astonished when we saw this. We could hardly believe it. Something so simple and has so little, it doesn't depend on much medical information at all. The medical information is contained in K1, which I'll say more about maybe next time. And K2 is automatically defined by K1. K3 depends on a representation of two biological objects as these chains. Yeah, so here we use a representation of F and G. For example, this could be given by a sequencing of from a double helix section, from a section of a double helix corresponding to a gene, a sequencing given by some X-ray spectrography or some microanalysis or otherwise. So we're using that representation as an amino acid chain here at this point. So that's where the biology enters in terms of the representation of these biological objects. And here. That's all. So what we do is we compare the kind of things we obtain from this kernel. K3 then is our final kernel on spaces of, I'll go into definitions next time in details, spaces of peptides. This is for vaccines. Peptides are used as vaccines. They're always peptides which are parts of viruses or fragments of bacteria. But nowadays, the pharmaceutical companies are putting a huge effort into developing vaccines from synthetic peptides. So what one can do is use data here from natural peptides to get predictions of peptide binding for big new classes of peptides, synthetic peptides, using this kernel, because here the basic geometry is contained in K3. And so by doing that, what we have done for the peptide binding problem, let's say for the fixed allele case, if we fix a variant of the gene, for example, in a particular population, then we can use a prediction method to say what are going to be the good vaccines to deal with that diseases related to that gene variant in that population. So we can do that, and so this is a big problem for vaccines. This has received a huge amount of study, and the best results to date were given by Martin Nielsen, who's, I think, just moved here to Buenos Aires in this university. And our results are a little more accurate than this big labs of Nielsen. But what's remarkable is they don't use any of the big amount of medical data that Nielsen and his group have put into their predictions. We've used only elements of biology that I've mentioned. Just the K1, the similarity on the amino acids, and the presentation of these, in this case, functions on peptides. Okay, so this gives a little bit of an introduction to the last two talks, the next talk especially, where I'll give full details of how one gets a peptide binding function from K3, and data given, basic data given on data sheets from the internet, where one knows some of the binding data, but want to get binding data for new peptides, and we'll see how that works. Well, the main thing is this K3. This is the main geometry we use to use a learning theory algorithm to obtain estimates for peptide binding, which are, I think it's fair to say, are state of the art. Okay, thanks very much.